Machine learning, scale. In machine learning, feature scaling, or simply scaling, is a technique used to standardize the range of independent variables or features. It is important in algorithms that are sensitive to the magnitude of features, such as gradient-based methods, example logistic regression, support vector machines, k-nearest neighbors, neural networks, and distance-based methods, example k-means clustering, principal component analysis. Why feature scaling is important. Many machine learning algorithms work better when the features are on a similar scale, especially when they involve measuring distances between points or optimizing over gradients. For example, distance-based algorithms, algorithms like k-nearest neighbors and k-means clustering calculate the distance between data points. If one feature has a larger range than another, it could dominate the distance measure, skewing the results. Gradient-based algorithms, methods like gradient descent in neural networks and linear regression will converge faster if the features are scaled. This is because features with larger ranges may cause the optimization process to zigzag, making it slower to find the optimal solution. Two types of feature scaling. There are two main types of feature scaling: normalization, min-max scaling; standardization, z-score scaling. A. Normalization, min-max scaling. Normalization scales the data to fit within a specific range, typically 0 to 1. Formula: snorm equals x smin max smin x underscore backslash text norm equals backslash frac x underscore backslash text min x underscore backslash text max, x underscore backslash text min snorm equals smax smin x smin. Where $x is the original feature value. Smin x underscore backslash text min smin and smax x underscore backslash text max smax are the minimum and maximum values of the feature. This technique is useful when you know the boundaries of the data and want all features to be on a uniform scale. B. Standardization, z-score scaling. Standardization transforms the data such that the mean of the feature becomes 0 and the standard deviation becomes 1. Formula: xstd equals x mu sigma x underscore backslash text std equals backslash frac x, backslash mu backslash sigma x std equals sigma x mu. Where mu backslash mu is the mean of the feature. Sigma backslash sigma is the standard deviation of the feature. Standardization is more robust to outliers and is generally preferred for algorithms like support vector machines or logistic regression. 3. When to use scaling. Normalization is preferred when the distribution of data is not Gaussian or when you want to preserve the distances or magnitudes between features. Standardization is preferred when the data follows a normal distribution and the algorithm assumes or performs better with standardized data. For example, in Python. Here's how to scale features using scikit-learn in Python. Python. Copy code. Import numpy as np. From scikit-learn.preprocessing import standard scalar, min-max scalar. Hashtag example data. X equals np.array, 1, 2, 3, 4, 5, 6, 7, 8, 9. Hashtag standardization. Scalar equals standard scalar. X underscore standardized equals scalar.fit underscore transform, x. Print, standardized data backslash n, x underscore standardized. Hashtag normalization, min-max scaling. Scalar equals min-max scalar. X underscore normalized equals scalar.fit underscore transform, x. Print, normalized data backslash n, x underscore normalized. 5. When scaling is not necessary. Scaling is not always necessary. For instance, tree-based algorithms, example decision trees, random forests, gradient boosting, are generally invariant to the scale of the features because they operate by splitting data based on feature values rather than distances or gradients. Naive Bayes and rule-based classifiers do not require feature scaling. 6. Handling outliers. If your dataset contains significant outliers, normalization may not be the best option since it scales data to the range between the minimum and maximum values, which outliers can disproportionately affect. In such cases, standardization might be better, or you could use robust scaling, which is less sensitive to outliers. Robust scaling formula. Robust equals x median, x, IQR, x, x underscore backslash text robust equals backslash frac x, backslash text median, x, backslash text IQR, x, robust equals IQR, x, x median, x. Where IQR is the interquartile range, the difference between the 75th and 25th percentiles. 7 use cases. Neural networks. Scaling is crucial for neural networks to speed up convergence during training. SVM, support vector machines are sensitive to the scale of the data, and feature scaling is often necessary for good performance. Clustering algorithms, K-means and other clustering algorithms work better when features are scaled since they are distance-based. Machine learning, train/test. Training and testing are crucial steps in the machine learning workflow. Training. Train a model on a portion of the data, typically 70 to 80%. The model learns patterns and relationships between inputs and outputs. Goal: minimize errors and optimize performance on the training data. Testing. Evaluate the trained model on a separate portion of the data, typically 20 to 30%. Measure the model's performance on unseen data. Goal: estimate how well the model will generalize to new, real-world data. Why separate train and test sets? Prevents overfitting. Models may memorize training data, but fail on new data. Provides an unbiased evaluation of model performance. Allows for hyperparameter tuning and model selection. Best practices. Split data randomly, but maintain class balance, if applicable. Use stratified sampling for imbalanced datasets. Ensure test data is representative of real-world scenarios. Avoid data leakage, no overlap between training and testing data. Python libraries for train/test split. Scikit-learn, sklearn.model_selection.train_test_split. TensorFlow, tf.keras.utils.train_test_split. Remember, proper training and testing are essential for developing reliable and generalizable machine learning models. Machine learning, decision tree. A decision tree is a popular supervised machine learning algorithm used for both classification and regression tasks. It splits the data into subsets based on the value of input features, creating a tree-like structure of decisions. The algorithm learns a series of if-then rules that lead to the predicted outcome. 1. How decision trees work. A decision tree consists of nodes, branches, and leaves. Root node, the top node that represents the entire dataset and the first feature used to split the data. Internal nodes, these represent decisions or tests on a feature that split the data further. Leaf nodes, these are the terminal nodes of the tree and represent the final output or prediction, either a class label for classification or a value for regression. 2. Splitting criteria. The decision tree algorithm selects the feature that best splits the data at each node. For classification tasks, the commonly used criteria for splitting are: Gini impurity, measures the probability of misclassifying a randomly chosen element. Gini, T, equals 1 sigma I equals 1 NPI 2 backslash text Gini, T, equals 1, backslash sum underscore I equals 1 caret NP underscore I caret 2 Gini, T, equals 1 I equals 1 sigma NPI 2. Where pip underscore IP is the probability of an element being classified to a particular class. Entropy, information gain measures the amount of disorder or uncertainty in the data. Entropy, S, equals sigma I equals 1 NPI log 2, pi, backslash text entropy, S, equals, backslash sum underscore I equals 1 caret NP underscore I backslash log underscore 2, P underscore I, entropy, S, equals I equals 1 sigma NPI log 2, pi. Information gain is the reduction in entropy after a dataset is split on a feature. For regression tasks, the most common criterion is mean squared error. MSE measures the average squared difference between the actual values and the predicted values at each split. 3. Tree building process. The algorithm recursively splits the dataset into subsets until one of the following conditions is met. All the data points at a node belong to the same class, for classification, or have a small variance, for regression. The maximum depth of the tree is reached. The minimum number of samples required to split a node is not met. This process is called recursive partitioning and results in a series of decision rules that represent the decision tree. For example of decision tree in Python. Here's how to implement a decision tree for classification using scikit-learn. Python. Copy code. Import numpy as np. Import pandas as pd. From sklearn.datasets import load_iris. From sklearn.model_selection import train_test_split. From sklearn.tree import decision tree classifier. From sklearn.metrics import accuracy_score. From sklearn import tree. Hashtag load dataset. Iris equals load_iris. X equals iris.data. Y equals iris.target. Hashtag split the data into training and testing sets. X_train, X_test, Y_train, Y_test equals train_test_split, X, Y, test_size equals 0.2, random_state equals 42. Hashtag create the decision tree classifier. Model equals decision tree classifier. Hashtag train the model. Model.fit, X_train, Y_train. Hashtag make predictions. Y_pred equals model.predict, X_test. Hashtag evaluate the model. Accuracy equals accuracy_score, Y_test, Y_pred. Print, F accuracy, accuracy *100.2%. Hashtag visualize the decision tree. Tree.plot_tree, model. 5 advantages of decision trees. Interpretability. Decision trees are easy to visualize and interpret. The tree structure makes it straightforward to understand the decision-making process. Nonlinearity. Decision trees can capture nonlinear relationships between features and the target variable. No scaling needed. Decision trees do not require feature scaling or normalization. Handles both categorical and numerical data. Decision trees can work with both types of data. Implicit feature selection. The tree inherently selects the most important features to split on. 6 disadvantages of decision trees. Overfitting. Decision trees can easily overfeed the training data, especially if the tree becomes too deep. This results in poor generalization to new, unseen data. High variance. Small changes in the data can lead to a completely different tree structure, leading to instability in predictions. Bias towards dominant features. Decision trees tend to be biased towards features with more levels or values, which can dominate splits. 7. Pruning. Pruning is a technique used to reduce the size of the tree by removing branches that have little importance, which helps prevent overfitting. 2 common approaches to pruning are: pre-pruning, limits tree growth by setting constraints such as maximum depth, minimum samples per leaf, etc. Post-pruning, grows the full tree and then removes parts of it if they do not contribute much to the final outcome. 8. Random forest and decision tree ensembles. To mitigate the weaknesses of individual decision trees, like overfitting and high variance, decision trees are often used in ensemble methods like random forests and gradient-boosted trees. These methods create multiple trees and aggregate their predictions to produce a more robust model. 9 use cases. Classification, spam detection, loan approval, medical diagnosis, etc. Regression, predicting house prices, stock prices, or any continuous value. Feature importance, decision trees can be used to determine which features are the most important in predicting the target variable. 10. Decision tree visualization. Decision trees are often visualized to better understand the decisions made by the model. This can be done using tools like tree.plot_tree in scikit-learn, or exporting the tree to a .dot file for visualization using graph-havis. Confusion matrix in machine learning. A confusion matrix is a visualization tool used in machine learning to evaluate the performance of classification models. It helps to understand how well a model has classified instances into correct and incorrect categories. Components of a confusion matrix. A typical confusion matrix consists of 4 cells. True positive, TP correctly predicted positive instances. True negative, TN correctly predicted negative instances. False positive, FP incorrectly predicted positive instances, type I error. False negative, FN incorrectly predicted negative instances, type 2 error. Example. Predicted class. Actual class. Positive. 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 Negative. Negative. Positive. Negative. Negative. Export to sheets. Metrics derived from a confusion matrix. Several performance metrics can be calculated from a confusion matrix to assess the model's effectiveness. These include accuracy, the overall proportion of correct predictions. Precision, the proportion of positive predictions that were actually correct. Recall, the proportion of actual positive instances that were correctly predicted. F1 score, the harmonic mean of precision and recall. Specificity, the proportion of actual negative instances that were correctly predicted. Formula for these metrics. Accuracy, TP plus TN, / TP plus TN plus FP plus FN. Precision, TP / TP plus FP. Recall, TP / TP plus FN. F1 score, 2 asterisk, precision asterisk recall, / precision plus recall. Specificity, TN / TN plus FP. Interpretation. High accuracy, the model is making correct predictions overall. High precision, the model is making few false positive predictions. High recall, the model is capturing most of the positive instances. High F1 score, the model is achieving a balance between precision and recall. High specificity, the model is making few false negative predictions. Visual representation. Confusion matrices can be visualized as a heat map or table for better understanding. Machine learning, hierarchical clustering. Hierarchical clustering is a type of unsupervised machine learning algorithm used to group data points into clusters based on their similarity. Unlike k-means clustering, which requires the user to specify the number of clusters in advance, hierarchical clustering creates a hierarchy of clusters that can be visualized using a dendrogram. This allows users to choose the number of clusters after the clustering process is complete. 1. Types of hierarchical clustering. There are 2 main types of hierarchical clustering. Agglomerative hierarchical clustering, bottom-up, starts with each data point as its own cluster and merges the most similar clusters step by step until only one cluster remains. Divisive hierarchical clustering, top-down, starts with all data points in one cluster and splits them into smaller clusters until each data point is in its own cluster. Agglomerative clustering is more commonly used and will be the focus here. 2 steps in agglomerative hierarchical clustering. Start with individual clusters, each data point is initially its own cluster. Merge clusters, at each step, the 2 closest clusters, according to some distance metric, are merged into a new cluster. Repeat, this merging process continues until all data points are in one cluster or until the process is manually stopped. Dendrogram, the process can be visualized using a dendrogram, which shows the hierarchy of clusters. The height of the branches in the dendrogram represents the distance between clusters at the time they were merged. 3 distance metrics. Hierarchical clustering requires a distance metric to measure the similarity between clusters. Common distance metrics include Euclidean distance, the most common distance metric, which measures the straight line distance between 2 points. Manhattan distance, the sum of the absolute differences of the coordinates of the points. Cosine similarity, measures the cosine of the angle between two vectors. Correlation, measures the statistical correlation between data points. 4 linkage criteria. When merging clusters, hierarchical clustering uses different linkage criteria to determine which clusters to merge. Common linkage methods include single linkage. Minimum linkage merges clusters based on the smallest distance between points in the clusters. Complete linkage. Maximum linkage merges clusters based on the largest distance between points in the clusters. Average linkage merges clusters based on the average distance between all points in the clusters. Ward's method minimizes the variance within clusters and tends to create clusters of similar size. 5 example of hierarchical clustering in Python. Here's an example of how to perform agglomerative hierarchical clustering and visualize it using a dendrogram with scikit-learn and scipy. Python. Copy code. Import numpy as np. Import matplotlib.pyplot as plt. From scipy.cluster.hierarchy import dendrogram, linkage. From sklearn.datasets import make_blobs. Hashtag create a sample dataset. X underscore equals make underscore blobs, n underscore samples equals 10, centers equals 3, random underscore state equals 42. Hashtag perform hierarchical clustering using linkage, Ward's method. Z equals linkage, X, method equals Ward. Hashtag plot the dendrogram. plt.figure, fig size equals 8, 6. Dendrogram, Z. plt.title, dendrogram for hierarchical clustering. plt.slabel, data points. plt.elabel, Euclidean distance. plt.show. 6. Interpreting a dendrogram. A dendrogram helps visualize the hierarchy of clusters formed during the agglomerative clustering process. Key elements of a dendrogram include vertical lines, represent the clusters. Horizontal lines, represent the merging of two clusters. The height of the horizontal line indicates the distance, dissimilarity, between the clusters at the time of merging. Cutting the dendrogram. By cutting the dendrogram at a certain height, you can choose the number of clusters you want to retain. For example, cutting the dendrogram where 3 horizontal lines are connected at the highest level would result in 3 clusters. 7 advantages of hierarchical clustering. No need to specify the number of clusters. Unlike k-means, hierarchical clustering doesn't require you to specify the number of clusters in advance. Produces a hierarchy. The dendrogram allows users to decide the number of clusters based on the data. Works well with small datasets. Hierarchical clustering is ideal for smaller datasets where visualizing the clustering structure is possible. 8 disadvantages of hierarchical clustering. Scalability. Hierarchical clustering is computationally expensive. Time complexity of O, n2, O, n-2, O, n2, or O, n3, O, n-3, O, n3, depending on the implementation, making it impractical for very large datasets. Irreversibility. Once clusters are merged or split, the decision cannot be undone. This can sometimes result in suboptimal clusters. Sensitive to noise and outliers. Outliers can greatly affect the resulting dendrogram and the clustering structure. 9 use cases. Genomics, grouping genes with similar expression patterns. Market segmentation, grouping customers based on purchasing behavior. Image segmentation, grouping pixels with similar colors or textures. Document clustering, grouping documents or text data into topics. 10 comparison with other clustering methods. K-means versus hierarchical clustering. K-means is more efficient for larger datasets but requires the user to specify the number of clusters up front. Hierarchical clustering does not require specifying the number of clusters but struggles with larger datasets. Scan versus hierarchical clustering. Scan is better at handling outliers and clusters of arbitrary shape, while hierarchical clustering excels at creating a hierarchical relationship between clusters.